Right, morning again folks. Here is the video of what we were speaking about earlier about capacitive reactance. So we say that capacitive reactance is the opposition to an AC current provided by a capacitor. The reason that an AC current is opposed by a capacitor is because a capacitor's function that we really haven't mentioned directly so far in any of your physics learning is what a capacitor does is it opposes changes in the voltage, and we'll speak a little bit more about that later on. You'll find the notes for this in the Bright Red book on page 106 or the Scholar Unit 3 topic 5.4. As we said earlier, the definition of reactive capacitance is the RMS voltage over the RMS current, and unit-wise that of course is, as it always has been, V for volts, A for amps for the current, and that of course means that capacitive reactance is measured in ohms, just like resistance, which is going to come in quite handy later on. This is the circuit that I was describing earlier. We have an AC supply, an AC ammeter, an AC voltmeter, and a capacitor, with the voltmeter across the capacitor, the ammeter in series, naturally as it would be. The main application, as we said, is to create an item called a high-pass filter, and what that does is in electronic circuits it will eliminate low-frequency signals and DC signals. So if we have, for example, a signal that looks something like this, and this signal would be a very small AC waveform imposed on mostly a DC signal. Well, if we take this waveform and we pass it through a circuit with a capacitor in it, then what we'll end up with is what at first look would seem to be not very much use, a very small waveform like so. So we've just removed the the DC part. We've removed the DC, we're left with the AC. So there's the AC bit just there, there's the DC bit there. So if we try and examine this, say on an oscilloscope, we're mostly looking at the DC because it's the bigger part of the signal. If we now pass it through the capacitor, we remove the DC part of the signal, we've just got this little AC bit left, and you would at first glance say, well, that's not much use because it's still not very easy to see. But if we're looking at this on a capacitor, what am I saying, on an oscilloscope, then what we can do is change the scale on the oscilloscope, and suddenly that turns into something more like this, and that is then much easier to examine and determine values for. So again, with the circuit, AC supply, AC ammeter, AC voltmeter, capacitor. First experiment that we would do if we were all together in real life, we would, for a fixed value of capacitor, vary the frequency of the supply. So I should really put an arrow through that to make it a variable AC supply. We would measure the RMS current with the ammeter. We'd do a graph of the RMS current and the frequency like so. RMS current on the y-axis, frequency on the x-axis. We would get a straight line graph through the origin, at least we should do. That tells us that the RMS current varies as the frequency. Since we know the reactance is equal to the RMS voltage over the RMS current, then from that we can deduce that the capacitive reactance varies as 1 over the frequency, and we'll come back to that for the third graph in a moment or two. The second experiment we would do, similar circuit, AC supply, AC ammeter, AC voltmeter, capacitor. This time for a fixed value of the frequency, so we're not using a variable supply this time, it's a fixed value frequency. We would change the value of the capacitor. That could be done either by taking out the capacitor and replacing it physically with one with a different value, or as I've mentioned before, there are variable capacitors in existence, and more commonly capacitor substitution boxes. So we'd be varying the capacitance this time. We'd measure the current through the capacitor and the voltage across the capacitor for each different value of capacitance. That would allow us to calculate the capacitive reactance. Then if we graph the capacitive reactance and the values of the capacitors that we used here, we'd get a nice asymptotic inverse relationship there, which tells us that the value of the capacitive reactance varies inversely as the capacitance. And then graph number 3, which is if we go back to what we found from, or would have found if we had done it, the first experiment, that the capacitive reactance varies inversely as the frequency, and we do a graph of capacitive reactance against inverse of frequency, we get a straight line through the origin, which is what we should have expected from our deduction that that's what the relationship would be. And then if we work out the gradient of this graph, we find that it's equal to 1 over 2 pi c, where c is the value of the capacitance. So if we put all three of those ideas together, we end up with the capacitive reactance is equal to 1 over 2 pi fc.